spray combustion, but I may be able to do a little bit with the droplet problem. So let me start with, so this is not relevant. So we're going to start with lecture 8, which is flame stretch and preferential or differential diffusion. Okay, may I start? Okay, so we we have seen yesterday that we can view on a large scale the flame as an interface, and we have seen that we can learn quite a bit from the simple idea that was introduced by Dario and Landau, which was a pure hypothesis that the flame speed is locally equal everywhere along the flame front to the laminar flame speed. The more advanced theories, which started really in the 1980s, have examined the problem using a multiscale approach or an asymptotic approach by exploiting the fact that the flame has a thickness LF, which is much smaller than the hydrodynamic length. I mentioned that yesterday already, so it's the same really approach, but now it's done formally. And so just to make clear what is assumed here in this approach is that there is a thin reaction zone, which is the reciprocal, the thickness is the reciprocal of the Zeldovich number, or the activation. It's driven by the activation energy, the fact that it's a large number, so the thickness is the reciprocal of the activation energy, and that the reaction zone is much smaller than the flame thickness, and delta is the ratio of the flame thickness to the hydrodynamic length, and that itself is small. So we have like one boundary layer inside another boundary layer, and that's the way that the problem was treated. The initial idea started with Clavin and Williams. They looked essentially at a perturbed planar flame, small deformation, small velocities, and so on. But then it went, the interest was primarily to advance the result of Dario and Landau, which I wanted to present first today, but we will talk about tomorrow, that a plane flame is always unstable. And so the idea was to try to improve on this result, which seems to be contradictory to experiment, because people have observed planar flame in the laboratory. And so the focus in the first two papers were directly, I mean, the focus in all those three pieces of work in the 80 or 82 was at the end of the day, to improve the stability result. The first two papers immediately linearized the governing equation using the multiscale idea and derive what we call a dispersion relation. You see all these terms, I will talk tomorrow. That's why I wanted to switch the order of things. But anyway, and that's how they got revised result for the stability theory. The work that we have done took a slightly different approach, but still using the same idea of the multiscale. We first derived the general model and then linearized the general model in order to study the stability problem. The advantage of this is that our model is not limited to perturbation of a planar flame. It can be applied to a spherical flame, a stretch flame, or any flame that you like. And so the model is quite general, and these days we are also applying this model to turbulent flames. So the fact that it's a more general model has been very useful in that respect. And the general model, or the general theory as I call it, leads to a nonlinear system, coordinate free form, so it fits any configuration you like. And it accounts for a variety of important effects, although sometimes I will present only the simpler version just for simplicity. So it accounts for thermal expansion, namely that there is significant change in density across the flame, that the transport are temperature dependent, so the conductivity, diffusivity, molecular diffusion are all temperature dependent, that the Lewis number are not equal to 1, which is what we refer to as differential diffusion. In other words, there is a difference between heat and mass diffusivity. And also the effect of what we call preferential diffusion, which means that the two species have different diffusivity or different Lewis number. It also accounts for effect of stoichiometry, because as we will see, there is an effective Lewis number that comes in naturally in the theory, and that depends on the equivalence ratio. And we can allow for reaction order, which are not necessarily 1, although most of the result that I will present will be with reaction order 1 for simplicity. And we can also incorporate some heat losses if necessary. So this is the idea, and I'm not going to discuss the mathematical detail, but essentially what you do is you the reaction zone and the flame and all the effects that's happening in this thin region are analyzed. Analyzed meaning we can solve the equation. The reason we can solve the equation is because when the flame is thin, is primarily the changes are along the normal. So the leading effect or the important effect are along the normal, but then we have also incorporated effects which are due to the flame thickness, which will result with transverse fluxes and perhaps accumulation within the control volume, the small control volume that describes the flame. So again, the idea comes from the discussion of yesterday that to leading order, the diffusion effects are negligible, but then we have incorporated them as a perturbation in the scheme. So all these effects are accounted for in the result. And, but the focus of the theory was primarily on the large scale. In other words, what we are interested in, what happened in the fluid flow, and the result of the boundary layer are dictating some matching condition or jump condition across the flame front, which effectively describe what's going on inside. However, having said that, it doesn't mean that we don't have the detail inside the reaction, the flame, and we do, and I will describe some of these effects as well. So as I said here, the focus of the theory was on the hydrodynamic zone. So essentially what we have is the Euler equation as we had yesterday, but with a small viscous effect as a perturbation. Instead of the Rankine-Hugoniot relation across the interface, we have correction to the Rankine-Hugoniot relation, which are taking into account the fact that the flame is not a true interface but have some thickness. And the last bullet is that the flame speed that we obtain is not just the laminar flame speed, but it's the laminar flame speed corrected by the local flow condition via stretch, which I will define in a minute, and it's modulated by a coefficient that depend on the mixture composition, diffusivities, and so on, which we refer to as the Marxian length. So I just describe in words what I will show you in a minute. So the flame is in, looking on the global scale, the flame is an interface. The interface is described by this function f of space and time equal to 0. So the flame move and change shape clearly. We have talked about the flame speed yesterday, which is the relative velocity of Vf to the incoming flow. So in the hydrodynamic zone, the equation that we need to solve are essentially the Navier-Stokes equation with density rho u on this side and density rho b on that side. The viscous terms are there, but they are a small effect relative to the inertia. And across the flame, we have, as I said, correction to the Rankine-Hugoniot relation, which I did not write explicitly. You can find them in the paper. And finally, probably the most important piece of information that we will expand the discussion on today is the flame speed. The flame speed turned out to be equal to the laminar speed corrected with the flame stretch and the Marsden length. So let me define now these terms. Flame stretch. First of all, yesterday we already saw two simple examples of flame stretch, an expanding flame and a flame in a stagnation point flow. In general, is a flame which has a three-dimensional surface as described here. The stretch is defined as we did already yesterday, the fractional area change of a Lagrangian surface element on the flame surface. So if this green area is A at time t, at a later time, because these points are all moving with the flow or stretched by the flow, or the flame is propagating, they change position and the area become A at a later time, t plus delta t. And so in order to obtain an expression for stretch, the idea was very simply to calculate A of t for a general surface with the intrinsic coordinate being the normal and the tangential E1, E2 to the surface, calculated at a later time, and produce the derivative and just evaluate this expression. The detail must be found in the paper, but here is the result. The result, and we can, I'll show you that we can write stretch in more than one way, and this is one way. The second way, equivalent to second way, I will show you in a minute. So the flame stretch contain a term here. By the way, stretch have a unit of 1 over time, clearly, as you see from the definition, right? So the first term is the curvature. Kappa is the curvature. The curvature of a surface can be simply obtained by the divergence of a unit normal. The negative sign is simply because we chose the normal pointing toward the burning gas. In general, the curvature is every surface have two principal curvature, and the curvature is the sum of the two. Some people call that the mean curvature because really it's the mean of the two, but it's a simple word to just use curvature. For example, a sphere, if you cut it in any direction, the radius of curvature will be always the radius of the sphere, and so clearly the curvature of the sphere will be 2 over r, right? 1 over r plus 1 over r. For a cylinder, let's say, one of the principal curvature is the radius, the other one is just the flat length, so it's 0. So, and for any surface, you can find always the two curvature, but you can compute it directly from the divergence of a unit normal. The second term is the strain. So the first term would correspond to like our spherical flame that expanded and the curvature, right, or the radius have changed. As a result, the flame is being stretched. The second term is the strain rate, which is acting on the surface, and this is obtained from just taking the strain rate tensor, dotted it with n and n on both sides. The example that I showed yesterday about the counterflow or the stagnation point flow is an example where it is the strain that stretch or cause the stretch of the flame. Okay, another way of obtaining this stretch rate, which turned out to be a very convenient way, simply because it's easy to compute, is written here. The first term is the propagation speed times the curvature kappa, and the second term is the curl of V cross n dotted with n, which is essentially the gradient along the surface, okay? S represents the surface, Vs is the velocity component along the surface, which is a vector clearly, and this is the gradient along the surface. The two are equivalent, but they are not identical in the sense that don't compare this term to this term, because here there is also a component of curvature involved. Another thing which is important to know is that the way that flame stretch is defined is consistent with the hydrodynamic theory, that the flame is uniquely defined by the surface F. Once you have, the stretch rate is the stretch rate of that surface. If you compute it from below or from above the surface, it's the same value. It doesn't have a discontinuity. And also, it uses the fact that the divergence of the velocity is 0 upstream and 0 downstream, because this is what the equation in that limit tell us, right? So if one wants to apply that using a different interface as representing the surface of the flame, you have to be careful, because first of all, there is some expansion on that surface. Second, it may not be continuous, and there could be many other things. So in general, it's a little ambiguous in the same way that it is ambiguous to talk about flame displacement speed by choosing an arbitrary surface. Okay, so this is another way to understand perhaps flame stretch is written here, where, what I have done is just decompose this strain rate, okay, this strain rate part into two, which is these two, okay, these two contribution. So as I told you earlier, in that strain rate, there is also a piece that depends on curvature, and so here it is. So if you look at it in this way, there are three contributions. The first one is the fact just that as the flame propagates, the curvature can change. The second one and third one can be understood if we look at this segment of the flame. Suppose that we look at this segment here where the curvature kappa is negative. Okay, you see the radius of curvature is toward the unburned gas, whereas in my notation it's pointing toward positive, the burned gas, so that's why it's negative. Okay, so it's negative, and suppose that you have a velocity field which the normal component looks like the arrows that I have shown here. So the normal velocity is positive, right? And if you multiply it by kappa, you get a positive contribution. So a flow which is diverging is going to be stretching the flame, right? In contrast, this flow here, which is converging, you see the product is negative now, and this flow will be contracting the flame, or it will be negatively stretched. The picture on the right explains the last term. The last term, as I said, is the gradient along the surface. So you see that here the gradients or the velocity along the surface decrease, so the gradient is negative, and so the flame is being compressed, and in this part is being stretched. So this part will be like a front stagnation point flow. This part will be like a rear stagnation point flow, a problem that I didn't discuss, but you can imagine what it looks like. The problem is that in combustion you cannot establish a flame in the rear stagnation point flow. It gets blown off, and so it's not a very stable situation. Okay, so this is so much about stretch. I went here in the next few slides through the examples that we said yesterday. We have seen that we can define stretch for the spherical flame. We have seen that from the definition, we get immediately 2r dot over r, right? We did that yesterday. And so if you compute this from either one of those formula, you obtain the same result. From the formula that was written on the right before, that term is 0 because the flow is radial, right? The flow is only in the radial direction. There is no component along the surface. And so this is 0. And Vf is the propagation speed, which is r dot. And so clearly the result is going to be 2r dot over r, as it is from the basic definition. In the second part, in the second version, what you see is the curvature term here is 2 over r times SL. And the strain, there is a component which is a normal strain. And the normal strain is, you can in fact compute it here what it is for the flame given the velocity that I computed yesterday. And so if you add them together, you get again the same result. So either relation, either expression gives you the correct stretch rate, which is 2r dot over r. For the, okay, that we said yesterday already. For the simple straining flow that I've described yesterday, we have seen again that the stretch is 2 epsilon, where epsilon was the strain rate, right? And this was basically from the definition itself. Again, here we can look at the two expressions. The flame is not moving, is stationary in this case, so Vf is 0. And this is the component, the gradient along the surface, which is the derivative of V with respect to R. And the 2 is just because it's a axisymmetric case, so you get twice that contribution. In the first relation, there is no curvature. The curvature is 0. And the strain is 2 epsilon, so that's immediate. Of course, those are two very simple situations. Canonical, maybe example of stretch flame. A general surface will have both contribution and, okay. So this I said. Here is just an example, and I have a few other examples in the quoted paper. If you assume that the flame has a shape of a cone, you will see that the two radius of curvature are r divided by cosine alpha, where alpha is the opening angle and the second one is infinity. And so the total curvature can be computed, and this is the stretch rate. So the cone is negatively stretched, okay? And the stretch rate vary depending on the incoming velocity, because of course it changed the gradient of velocities and so on. Okay, so this is an example. You can later look at it. Now I want to talk about the Marxian lengths. Again, remember that this is all obtained through a derivation, a detailed derivation of the solution inside the flame zone. So it's not, there is nothing here postulated or assumed, or sometimes people see the number effective and think that somehow it was created in some effective. No, everything was derived, okay? There is no ad hoc or any input outside from what you obtain from the derivation. So the Marxian lengths turn out to be an expression like that, and it depends on multiple things. The first thing is, you know that it is proportional to the flame thickness LF, okay, which was defined yesterday and it's written here, which means that the effect of the Marxian lengths come from the detail of the flame thickness, and it has the same magnitude as the flame thickness. Okay, the same, but this is important. So for example, we have learned that for premix flame, if you change the ambient pressure, the flame always becomes thinner, right? Okay, so you can in fact interpret the dependence of the Marxian lengths of pressure through this relation, because LF depends on the pressure inversely. Okay? So this is one comment to make. The second thing is it depends on the thermal expansion parameter, which is the ratio of the unburned to burned density, sigma. It appears, as you see, in all the expression. It depends on if you assume that the transport lambda is a function of temperature, then it depends on that functionality, which is usually T to some power. And so all you have to do is just to put the appropriate power. So for example, if it's T to 0.7, which is approximately correct for air, then you put x to the 0.7 divided by x, and you integrate that, and similar. So these are all numbers, right? Because they are definite integral from 1 to sigma. The next parameter is the Zeldovich number, beta, or the activation energy parameter. Of course, it comes in because we have assumed that that's the representation of the reaction zone thickness, and so clearly that will show up in the expression. And finally, there is a Lewis number here, but it's an effective Lewis number, and I would explain what that is in the next transparency. So before, or in the next after this. So here I just wanted quickly to show you that one can in fact, if you assume that the transport property are constant, diffusivity is constant, diffusion coefficient are constant, some of those integrals are easy to do. So for example, the first one, 1 over x, gives you a log, so it's log sigma. And then the other integral gets simplified, but it still needs to be maybe performed numerically. By the way, that integral is nothing more than a curve that goes like this, and it vanishes at don't remember where. Anyway, it's a curve that goes like that. Doesn't vanish. It's always positive. Sorry. If you assume t to the 1/2, you can still write an exact expression. If you assume it goes like t, so you see in reality it's going to be somewhere in between these two, or these three if you want. But really the detail doesn't matter. This doesn't change in any qualitative way the result. Okay? What change in qualitative way the result is the effective Lewis number, and I will discuss that in a minute. But what did I mention here? I said that the Marxian is positive. Yeah, the Marxian lengths will change sign depending on the Lewis number. If the Lewis number is bigger than 1, it's always positive, right? But if the Lewis number is sufficiently negative, I'm sorry, not negative, sufficiently less than 1, then that term will be negative, and the Marxian lengths can be negative. The Marxian length is just a coefficient that have units of lengths. It's not a length, so it can be negative. So the critical value is written here. So in other words, it's slightly below 1, okay? So if the Lewis number is slightly below 1, the Marxian lengths can be negative. All right. Effective Lewis number. The effective Lewis number. The theory have assumed that yes?
Yeah, I mean, I don't know why you have to define the new length scale like Marxian length in the first place?
I did not define any new length scale. What I obtained in the derivation is that the flame speed, SF, is equal to a constant, SL, minus a coefficient that multiplies stretch. Since stretch has units of 1/2, and this is centimeter per second, then the coefficient has units of centimeter, it's units of length. I did not define it, it's just what the coefficient came out to be. Okay, so again, the theory started by assuming that that there are two components. By the way, one can extend maybe the theory, but it was never done, to maybe a reduced mechanism or a more complicated mechanism. The only thing that has been done in the literature was for one global reaction step and that you have two components, fuel and oxidizer, in different proportion. And so what turned out to be is that in the expression for the Marsden lengths, the combination of those two appear, of the Lewis number of the fuel and the oxidizer. It's just that they appear in a nice way that it was convenient to call it an effective Lewis number. And what it is, it's essentially what you see here. It's a sort of an average of fuel and oxidizer, but more heavily weighted towards the deficient component. So if, for example, you have this A is the deviation of the equivalence ratio from 1, right? If phi is 1, A is 1, right? So if A is 1, meaning that if you have a stoichiometric mixture, the effective Lewis number is just the average of the two, fuel plus oxidizer divided by 2. But if you are more on the lean end or on the rich end, then you will see that always the deficient one counts more, because if A is relatively large, the 1 is negligible compared to A, and then similarly, this one is negligible compared to this, and the ratio just gives you LEF. So in a lean, very lean mixture, the effective Lewis number, or the Lewis number that count more, is that of the fuel. In a very rich mixture, it's a Lewis number of the oxidizer that count more. And I wrote here the more general formula for arbitrary coefficients A and B. You see why I didn't want to present it first, because they involve all kind of complicated integral, but those are just numbers to evaluate, nothing more. Okay, here is the effective Lewis number for some selected fuel-air mixture. In fact, I will present only two. The first thing is that, remember that the theory was built on using Fick's law for the diffusion law. And Fick's law, the only way to justify it is if you have a mixture which is dilute, okay? Otherwise, you have to use the full Stefan-Maxwell relation. That's complicated, was not done in any theoretical study. So you assume Fick's law, so you a priori assume that the mixture is dilute. So if the mixture is dilute, when I talk about the Lewis number of the fuel, it means in a limit situation where there is a little bit of fuel relative to the abundant species. And when I talk about the rich mixture, it means that there is a little bit of oxidizer relative to the so the Lewis number of fuel and oxidizer that appear in my theory are these limiting values. And those I can compute. So a good estimate for the Lewis number of the fuel is 1.81, and for the oxidizer, it's about 0.9. And then if you just plug in, if you plug in this expression, you get the value for any value of phi that you want. And this is what this curve represents. Since the beta appeared as a parameter, we plotted for different beta, which are realistic values, and it seems that beta doesn't play a major role. What is more interesting is that it's a monotonic function that decay from, let's say, the value of the deficient component of the fuel, right? If you're on the lean side, towards a value which is the oxidizer side. But this is good for what was this? I didn't say. I think. You don't say it on that one either. Did I say? If I remember correctly, it was propane, but is it written somewhere? Anyway, I'm pretty sure that that's for propane. And remember that propane is a relatively heavy fuel, so the diffusivity is small, and so as the mass diffusivity appears in the denominator, it means that the Lewis number of the fuel is a large number. Okay? And what you'll see next is hydrogen. And again, it's not written, I apologize for this. And for hydrogen, you see that it's totally the opposite trend, because the limiting Lewis number of oxygen is very small. Oxygen is a light fuel, so the diffusivity is large, and 1 over large gives, thermal diffusivity divided by large gives you a small number. So the Lewis number of fuel is small, and then it increases monotonically towards what would be the Lewis number of the oxidizer in that mixture. And so what you see is that these two fuels have totally different behavior, and we're going to see that that's also observed experimentally. That has an impact or a result that we're going to see that even experiments show that. Okay, this is just a graph of different Marxian lengths. You see that not only the hydrogen is one that increased, but also methane is such, but all alcohol and other hydrocarbons are more heavy, and they start with a high number and decrease as you change the equivalence ratio. What is plotted here is the Marxian number, which is the Marxian length divided by the flame thickness. Okay, so it's a dimensionless number. Note, by the way, that for hydrogen, for example, the Marxian number can be also negative, right? Okay. So the theory have shown the dependence of flame speed of flame stretch, showing that the relation is basically linear. So SF is SL minus L, the Marxian length, times kappa, the stretch rate. And based on this expression, right, which is actually written on the blackboard, if the flame is positively stretched, okay, then the flame speed will decrease with increasing stretch, provided L is positive, okay? But it will increase with decreasing stretch if L is negative. And that's what you see here for hydrogen air. Remember that for the lean case, the Marxian length was negative, and so it increased with increasing stretch. Okay, whereas the behavior for a rich hydrogen air mixture is just the opposite. All right. Now, I mentioned that yesterday in passing, but since we didn't discuss this relation, I sort of skipped it. But this is another way that people have attempted to measure the laminar flame speed. What you do, you put your experimental value for different, this is a counterflow flame, so you increase the flow rate, that changes the strain rate, and so it changes the stretch, and so you have different value. Of course, the flame is established closer and closer to the stagnation point as you increase the velocity or increase the strain rate. Or vice versa, it moves away if you decrease the stretch rate. And people have extrapolated this line, assuming the linear relationship down to 0, and the value should be the laminar flame speed. All this is correct. There's one point to make, that remember, the theory tells you it's true when the flame collapsed into a surface, and in experiment you are measuring things at a certain location. So if that location is consistent or not, it's questionable. So there is some ambiguity there, but people have over the time, well, that caused quite a bit of controversy and some problem in the early days, but that have sort of been cleared over the years. Here is the case of a propane, and since propane behave exactly opposite to hydrogen, you see that for the flame speed decrease with increasing stretch for lean and increase for rich. Okay? Okay, the next comment here is that one can write, I told you that sometimes people like to define flame speed relative to the burn gas as opposed to the unburned. Well, if you define the flame speed with respect to the burn gas, so first of all, you have to introduce the ratio of the density unburned to burned, so the propagation speed will be sigma times SL if you don't account for stretch. But if you account for stretch, then there is another coefficient here, a Marxian length, but that's not the same as the Marxian length for the unburned side. So that one is referred to as the burn Marxian length, and here is the expression. The relation between the two that I have mentioned is written here. Now, some comments. And these comments are quite important. So the first one is that something that I have mentioned already, that the flame speed or displacement speed has a precise meaning when the flame is planar and propagates steadily. For multidimensional and time-dependent flame, the definition becomes ambiguous. It has a meaning in an asymptotic sense, but otherwise it's ambiguous because the mass flow rate through the flame varies. And so it depends which isotherm or which surface you select within the flame to say that this is my flame front and that's the speed of the flame. Okay. The next, but as I said, it's uniquely determined in the asymptotic sense. Okay, the weakly stretched flame, for weakly stretched flame, we found that there is a dependence of the flame speed on the local flow condition and mixture condition. Flow condition through stretch, mixture condition through the Marxian length via this linear relation. And the proportionality coefficient is known as the Marxian length. Now, if the relation is not linear, I don't know what you call the Marxian length. Some people attempted to say there is a nonlinear relation and so on, but it became a little ambiguous and not very clear. So clearly, there is a clear definition when the relation is linear. Another important comment is that, which I mentioned yesterday, in more general circumstances, what I mean by this is that if the flame is not weakly stretched, which is often the case, right? The relation between flame speed and flame stretch is not known. So I have seen in the literature people argue, oh, here we have seen a case where the flame speed and flame stretch is not linear. Big deal. It's not linear because the flame is not weakly stretched. I mean, you cannot take a certain theory and believe that that theory is true under all circumstances. Okay, the flame speed in the hydrodynamic description can be defined relative to the unburned gas or relative to the burned gas. Now, since the flame speed, this is another set of comments. Since the flame speed depends strongly on the isosurface representing the flame surface, then the definition of Marxian length also becomes ambiguous because it depends on that location. And so, again, it's uniquely determined only in the asymptotic sense. In any other circumstances, the Marxian length will take a different form. In other words, if I want to choose now if my flame has this thickness and I want to choose this as the interface representing the flame, fine. But the relation will be different, and I will show you how. Also, it's not clear that along any interface that you choose, the relation must be linear. It's not necessarily the case. It just could be, but it doesn't have to be. So that's another thing to keep in mind. So, well, okay, from the simple hydrodynamic theory, where the flame is a surface, we have identified two numbers that we can call L and LB, right? One is evaluated from the unburned side, the other one from the burned side. But in reality, there will be many others, right? Depending on the location that you choose. And I will show you soon an example of this. Experimental measurement and numerical simulation of the Marxian lens evaluated at specific reference inside the flame zone is typically selected arbitrarily as an isosurface. Okay, I already said that. What did I say here? I mentioned that too. It's not necessarily true that the relation is linear. In fact, if you remember, yesterday I showed you that the velocity or the velocity in a stagnation point flow has this tooth shape, sawtooth shape. So here is the incoming flow, and then the flame jump up to a certain value, and then it goes down to 0 at the stagnation point. So people have found convenient to choose this minimum velocity as being a reference point simply because it's easy to measure. That makes a lot of sense. Unfortunately, it turned out, and we show that in this paper, that at this point the relation is not exactly linear, but it's more like stretch k multiplied by the log of k. Again, because there is no a priori evidence that at any location the dependence is linear. The reason for this is because at this location the temperature, if I draw here the temperature increases like this. And at this location, there have been enough of gas expansion that have caused a variation in the velocity field. And since it's the velocity that you are measuring at the flame speed, of course, it could be different than what it would be further ahead of the flame, where it would be here, where it's almost a linear relation. Okay. For a meaningful comparison, one must obtain the Marxian length from the inner structure of the solution, namely from the asymptotic details of the solution inside the flame, as I have described here. And this has been done. And as I said, provided, of course, the dependence is linear. So here is an example that I will focus on, which is a spherical flame. But first, the results here are not related to a spherical flame. They are general results. So what is shown here is the mass flux across the flame, but throughout the flame. In other words, there is no discontinuity here because you can evaluate this value at any location inside this boundary layer. This is what we called in asymptotic a composite expansion. It's an expansion which is valid all the way through, okay? Because very often when you construct solution, you construct what we call an outer solution, which is part of the domain, the inner solution, which is a solution inside the boundary layer, and very often it's hard, and then you want to match them, but it's very hard to create one solution which is valid throughout. But sometimes it's possible. In this case it is, and that's what it looks like, where the theta here is the temperature. It's a scale temperature, but it's a temperature at any location that you want. And so because I have such a relation, I can evaluate now the Marxian length at any location. But when you do that, it's more convenient for purpose of comparison not to plot the flame speed, but the density-weighted flame speed in such a way that on the burn side, it's exactly what people define the burn velocity. On the unburned side is also what you call the unburned. So on the unburned side, it's going to be rho, the star meaning at a temperature theta star. So on the unburned side, theta star is 1, rho star is rho u, and that's just flame speed. On the burn side, this will be rho b. Rho b over rho u is that sigma, the coefficient. And at any other location, it's the, the specific, the value of rho at the temperature theta star. Now, if you use this, then you can see that one can write an expression for the displacement speed of any isotherm, and this is the form it takes, so that you have an expression here that multiplies stretch and an expression that multiply curvature that are not necessarily the same. And this expression depends on which isotherm you choose. And so is there a relation like this, that flame speed is a constant plus a coefficient that multiplies stretch? Well, it's only true if curvature and stretch are proportional to each other, because then, of course, you can replace one by the other and write one single expression like that. An example of this is the spherical flame. And so this is the example that we are going to do. So for a spherical flame, kappa is 2 over r. The stretch is 2 sigma SL over r. You see that they are proportional to each other. And so if you replace kappa by k, you get a single expression that flame speed, a coefficient, stretch. That coefficient is any isotherm that you want. All right. Now, here is the spherical flame. And the solution that we wrote yesterday did not account for this contribution of LF. Everything is written here in dimensional form. And so the contribution of LF is the new contribution that I added by assuming that the flame speed depend on stretch. Okay? And what's interesting is that the new contribution doesn't only show the asymptote here, as we showed yesterday, but the solution, which is the red curve, show even the approach towards the equilibrium. The blue curve is the numerical solution. The red curve is the asymptotic solution. Of course, the asymptotic solution will start to deviate significantly from the numerical solution when the flame is very small, because the whole theory is built on the fact that the flame is large compared to its thickness. So it works after you have reached maybe 5 to 10 radii, okay? Oh, I mean, when you reach 5 to 10 flame thicknesses. The radius 5 to 10. Okay, so this is one comment. The other thing is we can write for the propagation speed, as I told you, which is what in the figure, which is not only the asymptote sigma SL, but also the correction due to stretch. Now remember that the correction due to stretch is when the flame, it's like the early time, not the later time, the early time, because then the flame is highly stretched and slowly it becomes less and less stretched. Okay, and what appears in this expression, just for because that's how immediately the result is obtained, is the Bern-Marxian length, LB. Okay, so the next thing I wanted quickly to show you is, remember yesterday I told you that depending on the equivalence ratio, you can have a situation where the flame accelerate towards the equilibrium or decelerate towards the equilibrium. In other words, eventually it propagates at a constant speed, but first it accelerate or decelerate. And the blue numbers are all when it accelerates, the red one where it decelerate. The transition occur at a somewhere around what? Between 1.3 and 1.43. All right? And this is what you get from the asymptotic theory. Again, there is a transition which occur around the same or in the same range. Okay. Next, this was taken from a recent paper with some of my collaborators at Aachen, and they have actually measured the dependence on of the propagation speed as a function of radii. And you see these are the measurements, and this is what the theory gives you, and it's quite remarkably close. Okay, now here is an important thing to try to understand. The focus of the hydrodynamic theory is on the global flow. So the whole flame, which is this region, in that limit have to collapse to a surface. So when it collapses to a surface, what you effectively do is you extend the incoming unburned gas all the way to the reaction sheet, and then in order to have the correct solution on the burn side, you need a jump across there. So this is for the spherical flame, and this is the mass flux relative to the flame. So the burn gas now is on the left, because this is the burn gas trapped inside the sphere, and on the right is the unburned gas where the flame is propagating. And this is the mass flux. The red curve is the solution from the asymptotic approximation. The circles here is a DNS. It's a simulation that was done actually with a single-step chemistry, but it was also done with other situations, with more complex chemistry. And the blue is what I call the hydrodynamic theory. So this part, it's like extended in order to represent correctly the flow on this side and on that side, and this is the whole region that in a way collapse. So but what I wanted to show you here is that the composite expansion that I showed you earlier that I derived, in fact, is valid throughout the whole flame. Well, okay, I'm going to skip this. So I'm going to take another few minutes before I take a break. So here is now the flame displacement speed that I want to show you from numerical calculation, from this composite expansion that I claim. And okay, so the first thing is it's calculated for propane. This is a result of a DNS, okay? And what is plotted here is the flame speed. The tilde represent that it's density weighted as a function of stretch. And stretch is calculated here from the fundamental expression that 2r dot over r. So there is no ambiguity in where you define it or how you define it. The numerical results show that as the stretch rate becomes smaller and smaller, meaning as the flame becomes larger and larger, you're moving in this direction. First, initially, the dependence was clearly not linear, but eventually it collapsed into a linear curve that approached the speed 1 as it should. Okay, this is a result from the numerical calculation. The same numerical calculation have used one of those two expressions that I mentioned yesterday to compute the displacement speed. In other words, you use an isotherm as being the representative isotherm representative of the flame surface. And here are the results. If your representative surface is on the unburned gas, you get a positive slope. If it is on the burn side, you get a negative slope. So which one is the correct? Well, that's the ambiguity that I mentioned to you earlier. Clearly, this one is the correct because that's what the more fundamental answer that I showed you here show. So this indicates that if you select an isotherm which is very far on the unburned gas, you are missing the correct behavior of the flame. And this is true from these are calculation for spherically symmetric flame, axisymmetric, so it's either a cylindrical flame or a spherical flame, with using the energy equation or using the kinematic relation. So it doesn't matter which of these two you use, you get the same kind of behavior. In fact, it's true even if you use a single step or a detail mechanism. Of course, in a detail mechanism, the data is more dispersed, but same behavior. So again, you get the wrong behavior if your selection is on the unburned side. And here is what the asymptotic theory tells you also. If you choose the theta star on the under. I didn't want to show you this first because I think it's more impressive to see it from the numerical calculation, but clearly it's the same trend. So this explains why, in fact. You see what happened is that the Marxian number on the unburned side is very sensitive to the choice of location, but then on the burned side it tends to more a constant number. And so the right way or the more systematic way would be to always pick it up on the burn side of the flame. This is essentially what is summarized here. A poorly selected isotherm may not characterize the combustion correctly. Okay, let's take a break. I think we're almost at the end of this, so let's take a break and then we will continue.